So I would like you to remember that one of the most important things we can do to make sure that we're seeing things well is to make sure that the stimulus is falling directly on our fovea. That's where we have the best acuity, that's where we have the best quality of sight. And a large proportion of what the eye is doing, and in fact what our attention is doing, is trying to focus that most important information right here on the fovea. That's where you're going to get the best information, that's basically where you're going to make the most sense of things, etc. The problem is that the world isn't that way. That is, the eye has to do a lot of things in order to get information kind of focused directly on that fovea. Light is divergent. It bounces around and it bends and all kinds of things as it's bouncing off of different surfaces and so forth. It reflects from those surfaces and it spreads out in all directions, so it's really hard for us to tell where it comes from. But thankfully our eye and the concave and convex lens enables us to reverse this spreading light and make it so that it focuses better into that single point on the retina, and in particular on the fovea. This allows objects that are near and far from the eye to be brought into focus on the same little point. That change in the shape of the lens, making it more convex or more concave, is called accommodation. So let's talk a little bit about how accommodation works. The lens itself adjusts its shape to bring the image into focus on the retina, and it's the ciliary muscles, which are muscles on the sides of the eyes here, that send information to the brain about the amount of accommodation that's happening. So basically you can see that when you're looking at something far away, our lens can become flatter. And when we're looking at something really close, it forces our lens to become more kind of fat, kind of round, etc., all so that we can focus that information on the same point here. Well, the ciliary muscles have to do a lot more work in order to make this thing more round, and as a result, it sends information to our brain that indicates that it's actually flexing a lot more, contracting a lot more than up in this situation where it's actually quite relaxed. When images are close, the light rays converge as they approach the eyes, and the muscles have to accommodate by making the lens rounder, and that's exactly what's happening here. But when they're far, the light rays can reach the eye more or less in parallel, and the muscles make the lens flatter. There's a point between these two things which is kind of a happy medium. It's called the resting point of accommodation. It's somewhere between these two extremes where the muscles are doing very little work at all. And of course you can imagine that's a nice situation for design. Often you want things kind of at that resting point of accommodation. One of the other things I think it's worth mentioning, especially in things like the design of spaces and things like that, I work a lot in the design of surgical suites and so on, is if people are required to look at something really close and then look at something really far away and really close and really far away again, basically one of the things that's happening is it's forcing your eyes to focus on a far point and a near point to become more concave, more convex, more concave, more convex. And the ciliary muscles have to contract and then relax, contract and relax. And that ends up really being quite fatiguing for the user in that particular case. So often it's helpful not to have people sort of switch between displays that are far away and then displays that are really close. So I think I just described this in the last slide, so I'm not going to go too much detail. So basically those ciliary muscles enable us to rely on a physiological depth cue. It tells us a little bit about how far away something is. So there's a number of ways to judge depth. I talked about one that's called accommodation. I'll talk shortly about binocular convergence and binocular disparity, but I think I'm going to talk about some other depth cues before that. Let's move to binocular and monocular cues for perceiving depth. So think about the world we're involved in. That's really a three-dimensional world, right? But our retinas are really two-dimensional. It's like looking at something on a sheet of paper, except that's the retina on the back of your eye. So the brain has to construct kind of this three-dimensional image from data that's falling on two dimensions. And it does that in a couple different ways. We have various cues for telling us how far away something is. One is monocular cues, or one type of monocular cues. That is, we can rely on one eye and still get that information. But the other requires two eyes. Those are binocular cues. And we're going to describe those here. So here are a couple monocular cues. One is called linear perspective. So if we look at two parallel lines, they tend to converge in the distance. Those things that are closer, it looks like a wider line. When it's far, it looks like a smaller line. That gives us some idea of depth. Those things that are far away along that sort of narrower line must be farther away. Another one is relative size. When two objects are assumed to be about the same size, but one appears to be further away, or one appears to be much smaller, we assume that it's further away. You can see that example here. Unless this guy is really twice the size of this fellow, it must be the case that this guy running around the bases is behind him and further away than him. So that's what's called linear perspective. We've got other ones though. There's interposition, or basically overlapping. You can see that here. You can see that this horse is in front of this other horse because it obstructs the vision, or our ability to view this other horse behind it. The same thing here, of course. That tells us that this one's closer to us than this one, and that one's closer to us than that one, etc. That's interposition, or overlapping. Another involves light and shadowing. So brightly lit objects tend to appear closer to us, and objects in shadows appear farther away. So that is kind of represented in this image here on our right. There are also issues like texture gradient. If we can see lots of texture, we assume that that must be up close to us, and if we can see very little texture, well, then that must be further away. And then there's aerial perspective and motion, which has a lot to do with sort of relative clarity and so forth. Things that are close to us tend to be clearer. Things that are farther away tend to be a little bit harder to see. So those are the monocular ones. Those require only one eye to figure out. But thankfully we have two eyes. So there's other information that goes directly to our brain that help us figure out how close something is. One is convergence. So if you have to look at something really close to you like this, your eyes have to turn in really close. Your eyes converge. You go cross-eyed basically. And doing that tells your brain that something must be really close. So if you come up here and look like this, your eyes go together, obviously that's really close compared to if it's out farther away and your eyes can be a little bit more parallel. The same thing with retinal disparity. We can kind of see things in stereo because our two eyes have a slightly different perspective on what it is we're looking at. So when I'm looking at my water bottle here, I'm seeing a slightly different angle from here as I am from here, and that tells me how much depth there is. In fact, if I move it really close, I see very drastic differences between those two things. If I move it farther away, my eyes are beginning to see something that's much more similar. And that tells us that when it's high disparity, when I'm seeing really different things, I must be really close to the object. Where I'm seeing less different things, it must be further away. Again, remember that our job here as designers and just in general is to focus as much of the stimulation that's coming into our eyes on the fovea as possible. And the fovea has lots of cones, whereas the periphery has lots of rods. A colleague named Stuart Ansis developed this illustration where he says, basically, if we think about what I'm looking at here is kind of foveated, I need something about this size. If I continue to look at here, as I come out further away from the fovea, further more peripheral on the retina, I need something this size to basically see it as well as something that's close and this size. As I go out further, I require something that size to detect it. As I go out further, something this size to detect it. So the idea is it's giving you kind of constant visibility if you're looking at this middle thing. It's just that with the periphery, I need something that's a really big stimulus over here to see it as well as the smaller stimulus right smack dab in the middle. Okay, so here's the idea here. In order to foveate something, in order to see something really well, it depends on a number of things. The first one is the size of the image. Now, the size of the image, when we're talking about eyes, it's going to vary quite a bit. One thing that makes it easy for us to see is kind of the visual angle of something. So the visual angle is basically tells us the size of the image on our retina. So the image size is determined by what we call visual angle. You can see over here the height of some object. Pretend, I don't know, let's pretend this is a beach ball over here and I'm trying to look at a beach ball. I want to know basically how big that is on the back of my retina, the size of it. That helps me figure out how well I'm able to see it. And the visual angle is calculated by the angle whose tangent is height over distance. And you can calculate it this way. Visual angle is 5.7 times 60 times height over distance. So here's the height, here's the distance, and the visual angle is 2 times the arc tangent of the height divided by 2 times the distance. So we want to maximize our bottom-up processing. Remember how well we can see the stimuli, or how sort of noticeable or salient the stimuli are. And in order to do that, we need to use things like, if we're reading text, proper text height. So titles and key elements that we're trying to show on a screen or show somewhere in the environment should be bigger than the smaller text that we want to read. Kind of the supporting text, the title should be bigger. So in fact, that should occupy about 0.5 degrees on our retina. That should be its visual angle. Dynamic or kind of critical elements that are part of that should be about 0.33 degrees, and static or non-critical elements like text should be about 0.27 degrees. But there's lots of other things that determine how well we're able to see and make sense of text. So here's another example. This refers to symbol spacing. That is the distance from one symbol to the next. If we're looking at this is a spacing ratio of 0.1 to 1. That is, the distance from here to here is about 1/10 the size as the distance from here to here, the height divided by the space in between them. So that's 0.1 to 1. But if we increase that size a little bit to about 0.25 to 1, we can actually see it from quite a bit farther. So it might not help so much if we're up close, but if I were trying to see a sign from further away, then I can sort of manipulate this symbol spacing, and that'll make me able to see it from farther away. This could be helpful if you're designing things like traffic signs or signage in a hospital or anything like that. We want people able to see it further away. Even things like menu boards at restaurants and things like that. Here's another example, stroke width. The print shouldn't be too fine. In fact, the stroke width of 1/6 of a degree of visual angle would be ideal. But wider is better, up to a ratio of 1 to 6. So here you can see a stroke width of about 0.1 to 0.8. So the stroke width is determined by the stroke of the character here, divided by the height of the character. But you can begin to see that a stroke width of 0.1 to 0.6 is actually a bit better. So a stroke width that is higher ends up being a bit better, up to about 0.1 to 0.6. Here's another example. The width to the height ratio, basically the wider is better up to the limit of the height. So here's a 0.6 to 1, 0.6 inches to 1 inch of the letter B. But if I wanted to see that from further away, I would go about 1 to 1. People used to ask me when I started out as a human factors engineer, they would always ask me, Russ, how big should my text be? And it always, of course, the answer was always, it depends. But one of the things that it depended on most was how much contrast you had. In this particular case, they were often designing things that were black text on a gray background. And that required a fair amount of fairly big characters. But I showed that if you could lighten up the background, you could take even smaller characters and make them much more visible. This is the power of contrast. So typically we want a contrast being the difference in luminance between the foreground and the background to be 7:1. So you can see here's a way of measuring this. We measure 3 points and average readings to obtain the luminance. And we do that for both the foreground around here, well, foreground around here because we're looking at the black as the foreground, and the background right here. And that should be between 3:1 and 7:1. Here you can see different situations with better contrast than others. You can see this yellow on the white in the back is really terrible to look at, even though we're pretty good at seeing things like green and yellow. The fact that there's so little contrast makes this really difficult to see. Here's another situation where there's really terrible contrast. It's important to do things like use a suitable font. So this is a situation where we're thinking about even top-down processes as well as bottom-up processes. Try to use familiar typefaces with little ornamentation. And typically we use sans serif fonts for digital displays. So sans serif fonts don't have little feet or little hats on them or things like that, whereas serif fonts do tend to have those things. So serif fonts are really useful for hard copy. If you've got a book, for example, that you're reading, it makes sense to have a serif font. In fact, this thing does, because there's so much resolution on text that doesn't exist necessarily on a screen that it works out well on text, but it doesn't work as well on the screen. Also avoid all caps. One of the reasons for doing this, especially in long strings of text, is there's just not enough variation between each one of the letters, so that actually makes it harder to sort of look at this and see the difference in the words in terms of the text. So here you can see there's lots of variation. There's a big T and a little I with a little dot on it, and little M and so forth. This variety is more than the variety here. This makes it much easier to recognize when you look at it. Also avoid confusing characters if you can. Lots of times we read something and type the wrong letter in response to it and so forth. So T's and Y's tend to get confused, S's and 5's, etc. These are just some highly confusable characters. And then finally, what if you really want people to see a particular thing? You really want something to attract people's attention. This is called conspicuity. So I use this example in the book, of course, but you're probably familiar with Where's Waldo? And Where's Waldo? Finding Waldo can be really difficult. And one of the things that makes it so difficult in most situations is he's surrounded by lots of other colorful characters, often in red and white and so forth. And, you know, it's a sea of sameness, basically. But if we just have Waldo and he's the only one that's in color, well, then it's really easy to find him. In fact, it's hard not to see him. So that's called conspicuity. When it's really critical for people to notice something, there are certain things you can do to make it noticeable. One is to make it flashing, another is to make it moving, and another is to simply make it different than those things in its surroundings. It turns out that making something flashing or making it moving, it's too conspicuous. It's almost impossible not to pay attention to it. So you want to avoid things like that unless you're, in a nuclear power plant or something and something is melting down. Well, in that case, you probably do want a flashing or a moving kind of signal. But in almost all other cases, I think just showing something as different than its background is still more than enough to attract people's attention to it. So I hope that gave you some good ideas for making things more visible, for improving bottom-up processing. Next, we'll be talking about improving top-down processing.